Here's a line-by-line walkthrough of the notebook. Step 1. Installing and importing libraries. Python. Pip install yfinance. Installs the yfinance package. Quietly, Q suppresses install logs. This library pulls historical stock data from Yahoo Finance. Python import numpy as np. Number.py, used here for array reshaping and numeric operations. Python import pandas as pd. Pandas, imported but not directly used elsewhere in this snippet. Yfinance returns a data frame internally, but the code converts straight to a number.py array. Python import yfinance as yf. The Yahoo Finance data fetching library, aliased as yf. Python from sklearn.preprocessing import MinMaxScaler. Imports a scaler that will normalize prices into a 0 to 1 range, which neural networks train on much better than raw prices. Python from tensorflow.keras.models import Sequential. From tensorflow.keras.layers import LSTM, dense, Dropout. Imports Keras Sequential API, a linear stack of layers, plus the specific layer types used, LSTM, recurrent layer for sequences, dense, fully connected layer, and Dropout, regularization layer. Python import matplotlib.pyplot as PLT. Plotting library, imported but not actually used in this snippet, no plt.plot, calls appear. Python import warnings. Warnings.filterwarnings, ignore. Suppresses Python warning messages, e.g., deprecation warnings, so they don't clutter the console output. Python print, QUANTNEURAL core environment initialized successfully. Just a cosmetic status message.
Step 2. Fetching data Python ticker equals ExxonMobil. Sets the stock ticker symbol to ExxonMobil. Python printf. Fetching historical market data for ticker. Status message. Python data equals yf.download, ticker, start equals 2018-01-01, end equals 2026-07-01. Downloads daily OHLCV, open/high/low/close/volume, data for ExxonMobil from January 1, 2018 through July 1, 2026, returned as a pandas data frame indexed by date. Python close_prices equals data, close.values.reshape, -1, extracts just the close column, converts it to a number.py array, and reshapes it from a 1D array, shape, n, into a 2D column vector, shape, n1, which is the format MinMaxScaler expects. Step 3. Preprocessing and scaling Python scaler equals MinMaxScaler, feature_range sadface 0, 1. Scaled_data equals scalar.fit_transform, close_prices. Creates a scalar that will map all prices into the range 0, 1, then fits it to the close price data and transforms it in one step. Note, fit_transform here uses the entire dataset, including what would later be future data, to compute the min/max used for scaling. Python x_train, y_train equals. For I in range 60, len, scaled_data. x_train.append, scaled_data, I60, I0. y_train.append, scaled_data, I0. Builds a sliding window dataset. For each day I, starting at index 60, it takes the previous 60 scaled closing prices as the input, x_train, and the price on day I as the target to predict, y_train. This is the standard. Look back in days, predict the next day. Framing for time series LSTMs. Python x_train, y_train equals np.array, x_train, np.array, y_train. x_train equals np.reshape, x_train, x_train.shape, 0, x_train.shape, 1, 1. Converts the list to number.py arrays, then reshapes x_train into 3D shape, samples, time steps, features, here, number_windows 60, 1, because Keras LSTM layers require input in that 3D format, 1 feature per time step, since only close price is used. Step 4. Building the model Python model equals sequential. LSTM, units equals 50, return_sequences equals true, input underscore shape sad face x underscore train dot shape 1 1. Dropout 0.2. LSTM units equals 50. Return underscore sequences equals false. Dropout 0.2. Dense units equals 25. Dense units equals 1. Defines the network architecture, layer by layer. First LSTM, 50 units, return underscore sequences equals true means it outputs a full sequence, needed because another LSTM follows. Input shape is 60, 1, 60 time steps, 1 feature. Dropout, 0.2 randomly zeros 20% of the connections during training to reduce overfitting. Second LSTM, another 50 unit LSTM. But return underscore sequences equals false this time, so it outputs just a single final vector, needed since the next layer is dense, not another recurrent layer. Dropout, 0.2 another regularization layer. Dense, 25 a fully connected layer with 25 neurons to further process features. Dense, 1 the output layer, a single value, the predicted next day scaled price.python model.compile, optimizer equals atom. Lost equals mean underscore squared underscore error. Configures training, uses the atom optimizer, adaptive learning rate gradient descent, and mean squared error as the loss function, appropriate for regression on a continuous value. Step 5, training Python print. Equals printf. Starting QUANTNEURAL predictive model training for ticker. Print cosmetic banner printed to the console before training starts. Python history equals model.fit. X underscore train. Y underscore train. Batch underscore size equals 32. Epochs equals 15. Verbose equals 1. Trains the model. Batch underscore size equals 32 means weights update after every 32 samples. Epochs equals 15 means it passes through the entire training set 15 times. Verbose equals 1 shows a progress bar per epoch. The return history object stores the loss value at each epoch, useful for plotting a loss curve, though that's not done here. Python